testing. So let's have some review about our last class, the last week. So as you know, we have two types of statistics. So the descriptive
Inferensial.
So when we have actually, when we do some research, use statistic, it will relate it to what we call data. So we want to have conclusion. Make a conclusion based on data. This conclusion can be generated or given by problem or questions. Mostly in engineering, the solutions or the process that we take is based on or driven by or triggered by problems. But for some scientists perspective, most process or research is triggered by questions. Some phenomena that they want to know what is the cause, or they want to answer. So that's the difference between engineering and scientists. And most of methods that we use both for the engineer or scientific or scientist is based on the data, and those process that we do, that's called statistics. Statistic itself can be divided into two types: descriptive statistic and inference statistic. We simplify it for industrial engineering because we will not use all those tools in depth for industrial engineering because most of our process in generating conclusion only will be based on problems. So these two types of statistic is for now is enough. But if you want to learn or study more about statistics, maybe you can learn or read about applied statistics or even mathematical statistics. Okay, so but for us, especially the bachelor degree, we only learn about descriptive and inference statistics. And the difference for these two, for descriptive statistics, we do what we call deductive process. So from populations, we will make conclusions about the sample. So based on later in descriptive statistics course, you will learn about the type of populations and how we can take or conclude about the context of a sample. On the other hand, for inductive, we will take or infer about the population based on the sample. How can it be? So actually in statistics, types of population already defined. So the scientists, like I mentioned before, they already raise a lot of questions about the type of populations, type of data. Then based on this type of population, type of data, they already generate many kind of model that we will know it as, or we call it as the probability model. So there are many kinds of probability model. And based on this probability model, then we can take some, because in each probability model we have some formulation. So using this formulation, we can then take conclusions or define or generate or take some decision for the sample. What is the sample? Sample can be in terms of like observation, kind of observation. Like for example, when you draw a coin, only there are two types of possibility of output or result. It can be the head or number, right? Most of the coins consist of usually the head, or it will just show a picture, and then the other side is shown a number. So when you throw a coin, the possibility of output only those two, whether it is the number or head. And many kind of conditions is based on those experiments. So like for example, like when you see games, only two types of result, right? It's like for example, football. Even though have so many goals, the decision only two, whether it's lose or win. Right? Another examples, like for when you go to take this degree, the result also can be defined only two, whether you graduate or you fail, right? So many situations that can be grouped as those kind of populations. And then the scientists define this every condition that have these two kind of result can be named as some probability model. Later, when you study about descriptive statistics, you will learn about the binomial distribution, geometric distribution, and then hypergeometric distributions, and so on. But for the other situations or conditions or populations, it's the possibility can be more than one or two results. For example, like for height or weight, it can be many options. That's why it's called continuous distribution. But for those, the result, actually no one knows, right? For example, when you go to, or when you first time join Universitas Brawijaya, you have like for this year 17,000 new students. I think in your year almost the same, right? Also like 16 or 17,000 new students. If you randomly take or choose one student and then you measure the weight or the height, the result can be any numbers, right? But mostly it will be in some range. So this is the height, for number of students. So most of the students, if you say most of new students will be in the range of age 17 to like maybe have some I think 20 or maybe 19, and some maybe just has age 16. 19 and 16 to 19 years old. In Indonesia, most of those, maybe we can divide into like male or female, but for nowadays I think have no significantly difference, right, for the age, because we also have like some female students also quite similar to the boys or male students. So we can say like maybe the average or the mean is around this 160, for example. So if you took it randomly, maybe it's like 60. Most of the students will have the heads for Indonesian students around in the range of 155 up to 165. Okay. Still, we have like the extreme one. Maybe for the heads, she or he only have like 140, and maybe we have some students like have the height 180, or maybe only have one student have height and up to 2 meters or 200, right? But it's only some people, or sometimes we call it outlier. Not too many, or not number of students. Okay. So we this kind of condition is not only for height or weight, but for some other situations, data will tend to have the central or for example, when we move to other region, for some, if we say in Asia, maybe quite similar. For example, we took sample for Singaporean or then Malaysian, or even in China, maybe we will find quite similar waves. But when we go to other region, like for we just say maybe Europe or Africa or India, they will have some shift, right? So for example, in Indonesia, if the range is 165, 160, maybe in some region it will shift like the mean will be like 170, 65, or even in others will have like in 170. But this type of conditions, this model is called normal distributions. So its data will tend to this kind of characteristic. they will have like some extreme data or outlier, whether it's the lowest or the highest. But most of it will have in central. Other examples, when you buy some products, they will like mention in the label. For example, you buy some sugar, for example. When they say 1 kilos of sugars, maybe you can take some random check. Actually, it will not have like, not exact all the package will have like exact 1 kilos, right? Maybe some will like have 1 or 1099. Some have 109, 0.95. Even others extremely will have only like 0.8. On the other hand, maybe have some more than 1 kilos, 1.01, 1.0. To an extreme, maybe if you lucky, you will get like 1.1 or 1.2 kilograms. Okay. Other example for drinks, if sugar or other solid product, maybe you will have difficulties to validate the volume. But for liquid, for example drink, just try to like how to say just compare like maybe 5 drinks in bottle. You can see some products really clearly difference, significantly difference the volume certificate. For example, like mineral water, the mineral water with brand mineral, okay, le mineral, you can see sometimes it's different or other brand as well. So it means they have like most of the product, it will have the as it mentioned in the label, but actually they have tolerate rates about the volume. Okay. Other examples for life expectancy, right? In Indonesia, maybe most of the life expectancy is like around 70. So means most of Indonesian people, it will like reach what we call it? Maybe in the means maybe around 50, but we have like most of them will like have life expectancy up to 70 years old. So we only have a few elderly people more than 70, because most of people will say like they feel already old after reach 50 years old. But in other countries, for example like in Italy, 70 is still young. So actually like they will just say they old after 70. And if you die on 60, they will say you died young. So they will say it's too bad to die in this age because it's still young. And we can see still many elderly like have or reach age up to 90. Okay, but in Indonesia maybe only like 1 or 2 people. So these two, so age or life expectancy also have tendency to be in normal distributions. And scientists actually already define that when we take data more than 30 data, it will tend to be in normal distribution. So every time you took, like for example, the drink, just take for 30 bottles, then just make like the chart, the lowest volume, and then this is the number, right? 1 bottle, and then 2 bottle, 3 bottle. For example, if 30 means like 15 bottle. So most of the data will tend to group in the middle and with the highest number of data, and this is become the mean. And for normal distribution, the mean and median will have the same number or the same point. Do you still remember what the difference between mean and median? Another one is modus. So actually, mean, median, and modus in this normal distribution will have the same point. Or almost similar, almost same. Do you remember what is mean, what is median, what is modus?
Mean is the average.
Mean is average. Both actually represent average, but this one, average, how can you calculate mean?
Divide the frequency.
Yeah, so the sigma, the total number, and then divide it into frequency or number of data or observation. And what about median?
The average
Is it total frequency divided by 2?
Yeah, total frequency divided by 2, so that's 5. So usually it will be in the middle. So if you like make it, some data will like this is the frequency, this is the value, right? So the lowest one, then how many number of data or the frequency, and then you put it based on the value from the lowest to highest. The middle one divided into 2 is median. And then what is the modus?
The largest number of data.
Yeah, the largest number of data. So if you have like, for example, this is the 30 data, half of data, or it actually not necessary half, but means half is in the middle, but the other then distributed into the other lower than the middle and higher to the middle. For the frequency, I mean, if you this, for example, this is 15, means the other 15 can be, for example, like 7 data may be lower than, for example, if this 8, maybe 15, so 7 people maybe die before 50 and the other 7 die after 50. But most of them, for example 15 or 16, is die when they reach age 50. But it not necessarily 15, it can be like maybe higher, like maybe 20, means the data should be like more skewed like this. Because the other 10, for example, like maybe 5 die before 50 and the other 5 die after 50. That's the simple example. But in detail, you learn it in statistic descriptive. So this theory, it's called CLT or central limit theorem. Means when you have more than 30 data, you can assume it as distribution, normal distribution. Okay. So when it considered as the normal distribution, you can process every this data using any formulation or any step or rules that based on normal distribution. Okay. So why this is very important? Because like I mentioned before in last week meetings, we have what we call parametric and then non-parametric. So parametrics is the statistic process that based on distribution model, the probability distribution model base. But for non-parametric, it's non-probability distribution model base. So discussed in this course. Why it's called parametric? Because when we inference, okay, inference means we take conclusions or infer some value based on, so for example, so we infer about population in inference statistic. We infer about population parameter based on sample, based on observation, observe data on a sample. Okay. So in inference statistic, we do the inductive side. So from sample, we conclude about the population. Actually, what conclusion that we take? The conclusion that we take is about the parameter. What is the parameter? So the parameter is is a value that represent those populations. So the parameter in populations, this one. Okay. There are three types of parameters that used to represent population and sample. Those are mean, variance, and then proportion. So, because when we talk about data, it's mean what we care about usually is about the mean, and then variance and proportion. Means is average, so like you will just care about the most number on those population, right? Like when you design a product, you will just see the average number of people. For example, when you design clothes, like mostly the size will be in a range of medium or large. Just a few numbers you will produce, for example, for the XXS or XS or S, but most will be the size of medium and large. But actually the medium and large in some region or countries will be different. Like for like the size, even the medium size for US and medium size for Asians can be different. Also for the example for size of shoes, maybe in Indonesia most of the size will be like range or for male 41 up to 42, right? But those size maybe will be like the outlier or the minimum for the other regions. Okay, that is the mean. So when we define a product, number of how many products that will be produced, we will care about the mean. Okay, so but sometimes not only mean that we care about, but also the variance. Variance is the difference. So like the for error, for like rejection, the defect. So when you produce a product, how can you define the rejection, the defect product will be based on the variance that you tolerate. For example, so if this is the volume, if you have the very tight tolerate, so you will like have the, and if the production process is really good, so you will only have like very small range, right, in the middle. Most of the product will like only have tolerate like, for example, 1 liter volume of water, but mineral water, the size 1 liter means the variance is very small. You only tolerate like 0.01 example. So less than 0.05, it will be categorized as defect, whether it's higher or it's lower. Okay, but if the process is not good, so the variance is high, okay, most of your product will be like have the range here, means you need to have more the higher range of tolerance. Okay. So some conditions will be conclude or concluded based on the variance. But some situations also can be concluded based on proportion. Like for example, how many percent that students can pass the statistic course only in one time, one chance take this course. Okay, because like statistic is quite difficult, so I think most of like almost like 30% will fail. Fail here means like the grade or the result will only get C or maybe C plus. So it's like 30%. The other 70% get like B plus or A. Okay. Means usually most of the students that get C or C plus they will take the summer course to increase or to because we don't have the remedial test. Means when you get C or C plus, you need to retake the course in the regular semester or just take it in summer course, or in our university we call it semester antara. Okay, so some conditions more pay attention about the proportions. So like the pass is 70% and then fail is 20%. And for the other examples about the maybe for productions, they don't want to know about the how is the variance, but they will like care more about the proportion, how many or how much percent that the product was was defect, and how many percent that the product succeed, okay, or good product. And you can imagine if you want to take conclusion about the population the parameter of this population, parameter from populations, if you do it to all the population, just to take to know about the mean of this population, how much cost that you need to prepare, and how much times that you need to or it will consume time, right? So like for example, you want to know the head of 17,000 new students head, means you need to measure all the students head, right? But actually, using this inference statistic, you can draw conclusion about these parameters of population only based on sample. So you just need to take like 31 sample, means it's already fulfill the requirement about the normal distribution conditions, and then you can use it to draw a conclusion about the mean of population. Okay, that's why we will like use different notation. So the population's mean, they will like use notation mu, and for variance they will use sigma, and proportion for populations they will use the P, capital P. But in sample, mu or mean, for sample it's X bar, and variance for sample use the notation S, and proportion for sample is the lowercase b. So what we will do in this statistical inference is we draw conclusion about this parameter in population based on what we get the information we get from the sample. So we draw about the mu or mean population based on mean in sample, and the variance of population based on variance we take from the sample, and the proportion of population based on the proportion from sample. And this parameter, if we draw it based on probability distribution model, it's called the parametric statistical inference. But if we ignore those distribution model, it's called non-parametric statistical inference. Because maybe on some condition, it's very difficult to find like 30 random data variables. So we cannot fulfill the requirement of this parametric inference statistic. Okay. So, the term that we will use in doing the inference or to infer in statistics, we call it the hypothesis testing. So the hypothesis testing is an assertion or conjecture concerning one or more populations. So actually, what we do in hypothesis testing, it can be for one sample or in basic. Actually, we only learn about 2 sampling. Later on, after the midterm, you will learn about more than 2 sampling. Maybe later, if you heard about ANOVA, actually it's a group of hypothesis testing for more than 1 sampling. Okay, but for now we will learn about 1 or 2 sampling. For 1 sampling means for one so we will infer or conjecture from 1 sampling about what I mentioned before. One population, but into sampling means we have 2 population. So sometimes we only care about 1 population. For example, like the mean of the height of new students, but sometimes we want to know about or compare to populations. For example, what you call what I suddenly forget what is IPK in English?
GPA.
The GPA, or for example the regular program, or compared to the IUP program, for example. So we want to know the difference. So whether the populations, the first population higher or higher compared to the other populations. Or for example, you want to, like, my hypothesis, actually for nowadays, there are no significantly difference between male and female hate for your generations. Okay, maybe in my generations, we can see the significant difference. So means we need to prove whether my hypothesis is true or not. That the hate or mean hate of hate for male and hate for female is actually similar or no significant difference. Okay. So that's what we will do. So in hypothesis testing, we will define two types of hypothesis. First, null hypothesis, and on the contrary is the first hypothesis or the alternative hypothesis. In defining the hypothesis, actually we do what we call in law, usually the judge will have presumptions of innocent until proven guilty. Presumption of innocence. So it's also used in hypothesis testing. So usually, actually what we want to know mostly is we want to prove that the alternative hypothesis is true. Okay, but then we use the presumption of innocence. Means that in null hypothesis, we will always define it as equal. But for the alternative hypothesis, we will define is can be lower than or lower and equal, or higher. Oh, sorry, higher or higher and equal than lower. Or not equal to some number. So if we want to prove that the mean means mu, and then the variance means sigma, and proportion is capital P. So, but for today or the first meeting, we will only discuss the mu. Okay, why always equal to in null hypothesis? Because we use the presumption of innocence. So actually we want to prove that for example, the height of the new students will be higher than 160. But actually, we have the presumption of innocence. Means actually not higher than 160, but it's actually equal to 160. And when it's failed, that's why we will call it recheck null, or not recheck H null, or fail to reject H null, or the null hypothesis. So it's not common to say accept the alternative hypothesis, but the term that we will use usually in statistics is reject null hypothesis, or fail to reject null hypothesis, because it's based on these conditions. Okay. So actually the null hypothesis is the defendant is innocent, and alternative hypothesis is the defendant is guilty. That's why we use term that reject null hypothesis, or fail to reject null hypothesis. Yeah.
For HO, is it hypothesis primary? For HO, is it primary?
It's not
Is it the hypothesis primary?
primary.
What is the definition of H?
Oh, so the null hypothesis, and H1 is the alternative hypothesis. So the definitions actually based on those I mentioned that H null, or the null hypothesis, it's innocent, and the H, or the alternative hypothesis, H1 is guilty. In terms of data, usually those are innocents. We will like use the mathematical or this equal means like this is innocence, right? So for example, in the case of male and female hate means there's no difference or innocence, right? But for the alternative hypothesis, we want to say or draw conclusion that it's guilty. Guilty means can be higher or lower or even not equal to. Right? So when you draw hypothesis, in null hypothesis, you will always use equal to, but for alternative hypothesis, only this alternative. Even though we can also use like what is the higher and equal up to equal to and lower up to equal to, or means not equal to, means we cannot define it whether it is, we don't care it is higher or lower, means when it's not perfectly equal, means it's not equal to. Okay, that's for the alternative hypothesis. The reason why null hypothesis always equal, it's based on the concept of presumption of innocence. Okay. So later on, whether it is the mean hypothesis testing or the variance hypothesis testing or proportion hypothesis testing, the rule is this. So for the null hypothesis, always use equal. So actually still have two types of errors, because like we draw this conclusion based on the sample. In like I mentioned in inference, we draw conclusion about population only based on the sample, right? Means if we take the wrong sample, we will have like the possibility to draw a wrong conclusions. For example, this is the populations. The good sampling actually, for example, this is the value. Okay. So actually you need to like take sample in each group, right? So for example, if you want to take 50, for example 31, because based on the central limit theorem, you need to gather at least 31 data or sample. Means you need to measure that the random is from the lowest one. You take 3, here you take 4, here 3, and maybe here 2, and here is 3. So if your sampling is like this, the possibility to get the all representative from the data is fulfilled, right? But it could be you only get like your sample is only here, but you miss this part. because you take it random, but not random enough, so you not in purpose to take only this group of samples. So when you draw conclusions, of course your conclusion will be in this range. But in reality, actually the mean of population is here. Or on the contrary, you take sample here, means you draw conclusion here. So in this case, it you can be took two wrong conclusions. So and this is already defined by the scientists. So there are two types of error. So actually we realize in hypothesis testing it's not 100% accurate. That's why we have an error. There are two types of error. First is alpha and the other is beta. Alpha is type 1 error and beta is called type 2 error. So type 1 error is that you reject the null hypothesis when actually it's correct. So you said it is not equal, but for example, for the cake, you reject the null hypothesis, which the hypothesis mentioned that the height of these new students, mean of the new students is 160. But actually, the truth or the real conditions, the null the height of this population is 160. When you reject the null hypothesis, when the hypothesis is true or correct. And on the other hand, you, for the type 2 error, you do not reject the null hypothesis when those hypotheses actually false. Okay. So to limit this error, we use the alpha. So the highest the alpha means the lowest the alpha means you tolerate or you include the longer range, because like the alpha is here. So usually like alpha is percentage. So if you want to limit the error, mean you need to make lowest alpha. So usually alpha will be in the range of 0.5. The lowest usually 0.001. So means if you use alpha 0.5, means you realize that there are possibility that 5% your conclusion will be false. When you reject null hypothesis when it actually true or correct. And means like when you say about alpha,
sorry, how can we know the alpha is like at 5% and at 0.0?
Actually, alpha is defined by ourselves. So, what alpha that you want to use, and the normal, some research allow the alpha up to 10%, or how to say it? 10% means 0.1, right? But most number of alpha that commonly used is 5%, and for the accurate is 1% or 0.101. Okay. Here means the confidence is 90% because confidence interval is 100% minus alpha. So if you use alpha 10%, actually you only confidence about 90% that your conclusion is true. But if you use the 5%, means your confidence interval is 95%. You can be or your confidence was your 95% of your conclusions is true. And if you want the accurate ones, means you need to use the lowest alpha. That means 99% is your confidence interval. You say it represents your rates. So alpha is here. Okay. So if you say you use alpha is 10% means you allow that, or you realize that you will not include those 5% in each side. So 5% lower than the mean, and 5% the outlier of the highest side, the higher side. So you will like say only in this range of the data, range of data. Okay. And for the lowest alpha, mean only small data that you allow to not be included in this observation. That's why you can say that your confidence interval is 99%. Means you conclude this or you draw the conclusion based on this 99% rates. See? That's alpha. So actually in hypothesis testing, the reason why we use like alternative hypothesis to be proved or to be proven, because actually we care when we draw conclusion in hypothesis testing. Actually we not draw one number of value, but we draw about the range. It's like, for example, the height is 160 and height is 100 and more than 160. Means the mu or the mean of the height of this population, we try to not define only one number, but range of numbers. Okay. And here later on we will like learn how we can draw conclusion which one is rejected. Do we reject the null hypothesis, or we fail to reject the null hypothesis? What then? When can we use the type 2 error? Actually, type 2 error, in this context, we will not utilize this kind of error, because this error will be utilized when we actually not in our inference statistic, but mostly applied statistic or in mathematical statistic. Okay. Because we already reached our time limit.